Hello and welcome everybody. I appreciate you joining us today for a session on measurement techniques with video borescope. Today we'll be spending some time with two individuals that are going to take you through some measurement techniques, as I just said. But before we start, just wanted to go over a couple housekeeping items. So as you'll notice on your panel, you'll see a number of different application engagement tools. These are all resizable and they're also movable. So you can just set up your screen however it's best for you to participate. And secondly, I want you to know we do have a tool that allows you to set up a demonstration. So you can have either a virtual or have one of our sales team come over and visit you and show you more about what you'll see today. Please take advantage of that if you'd like. The slide area, that can be maximized to full screen by clicking on the arrows in the top right corner, letting you know that. And then lastly, if you have any questions during the webinar, please submit them through the Q&A panel. We'll be monitoring them, and then as we get done, we'll spend some time on Q&A, and we'll let our two colleagues answer these questions for you. If for some reason we run long and can't get to all the questions, we will answer those and we'll send them back out on the email that you have logged in with. And then if you wouldn't mind, at the end, please take a couple minutes to fill out our survey. It helps us understand how well the message was received, the information was the right information. If there's anything else you'd like to see instead, that'll help us to make future webinars better and the content directed at what you would like to see. So with that, let me now pivot over and introduce you to our team today. First, Clark Bendel. Clark spent the last 24 years in this RVI business, and he's been instrumental in development of our image processing and much of our measurement technology. This is market-leading measurement technology that you're going to see today, and Clark's been a core piece of the team that has brought that to the market. And alongside Clark is Tom Danvers. Tom has been in the aviation business for over 20 years, developing ways to inspect gas turbines. Has worked all over the world doing this and has come up with numerous techniques to solve difficult problems that arise for folks that are trying to make a determination on whether to keep an asset in the air or not, or keep it online. And so with that, I'm going to hand it over now to Clark Bendel, who will kickstart the presentation for today. Thanks, Clark.
Great, thanks, Tom, and thank you all for joining today. So from an agenda perspective, we'll give a brief overview of our real 3D measurement technologies. And then I'm going to hand it over to Mr. Danvers, who will give us a number of application examples and show how those technologies can be applied. So first off, what are we referring to when we use this term real 3D measurement? This really encompasses a range of things, including a number of 3D optical tips, a suite of software measurement tools, a fully surfaced interactive 3D point cloud, which is kind of a foundational item for real 3D measurement. We have something we call a 3D surface mask, and then a dynamic advisory system. So all these things together are what we refer to as real 3D. So let's start by talking about some of the technologies related to those 3D optical tips. The first is traditional stereo, or simply stereo, which we've had available on our product since about 2002. It utilizes a stereoscopic optical tip that provides left and right views that are overlapping. The operator positions cursors in the left-hand image, and the processor finds the matching point on the surface in the right-hand image. The spacing between those matched points is less for points that are close to the tip than for points that are far from the tip. And it's that change in spacing versus distance that allows us to calculate a 3D coordinate at each cursor location. And then those 3D XYZ coordinates are used to calculate that measured result. So this is a 3D measuring technology, but it's not a real 3D technology because it doesn't provide some of those other features noted in the previous slide. So that brings us to real 3D stereo, which we launched in around 2015. This uses the same stereo optical tips, but applies much more advanced processing algorithms, which allows us to create a full 3D surface map and a point cloud, which we mentioned was sort of a cornerstone of real 3D. And then finally, we have real 3D phase measurement, which uses a phase-shifted structured light projection technology, again, to compute a full 3D point cloud. And the great thing about 3D phase is that it gives you a very high quality, full screen, wide angle field of view that works great for general inspections and gives you measurement on demand capability. So with stereo tips, an inspector would typically do the inspection with a non-measuring optical tip. And if they find an indication, withdraw the probe, switch to a stereo tip, and try to find their way back to the indication to make the measurement. So with 3D phase, typically inspections can be done all using one tip, or many inspections can, and therefore you save a lot of time and headache trying to get back to the indication. From a tip offering perspective, stereo tips are available on all diameters. 3D phase measurement is only available on the 6.1, and that includes a couple of general purpose tips, as well as a closer focus and a long range tip, which can be great in a lot of applications where you need to scan larger areas. So this brings us to our first poll question. If you wouldn't mind taking a few seconds to answer this one, which form of measurement do you use or have access to while undertaking your in situ inspections? So we're going to take about 30 seconds. If you could go through and just let us know if you have any of these available to you currently. And this could be on Waygate products, or if you have another system that might have a traditional stereo type capability. We'll give you about another 5 seconds here. All right, hopefully you've all gotten your answers in. All right, so it looks like currently we have quite a few traditional and 3D stereo users, quite a few 3D phase users. It's good insight. Thank you. Appreciate that input. Okay, so this brings us to the measurement tools or measurement types that we offer. The first 5 of these up to multi-segment, those are available on traditional stereo and maybe more familiar. The last 5 are only available with Real 3D on Waygate products, and many of these will be demonstrated shortly by Mr. Danvers. This radius gauge type is coming soon in a software release later this summer, and Tom will be demonstrating that as well. So before I talk about the other aspects of Real 3D, I wanted to take a moment to talk about common sources of measurement error in our types of applications. So first is capturing the image from too far away. These are triangulation-based systems, which means the accuracy decreases pretty rapidly as you increase the tip-to-target distance. So for best accuracy, you always want to try to capture the image from as close to the indication as possible. Next, having insufficient 3D data quality for the type of measurement you're performing. This is especially true with depth type measurements. And this can often be a result of capturing an image from too far away, but can also be caused by things like glare, surface reflections, oily surfaces, etc. Using the wrong measurement type can cause quite a bit of error. And so it's important for you to understand how the different measurement types work and how they should be applied to the different applications. And hopefully Tom's demonstrations will be helpful there. And finally, incorrect cursor placement. Most of the surfaces that would be measured on with our products are not just simple flat surfaces. They have complex 3D shapes. And so if you put your cursors in the wrong places, you will get an answer, but it may not be giving you the actual dimension you're interested in. So at this point, I'm going to switch over to our PC remeasurement software, Inspection Manager, to talk about those other three aspects of Real 3D. So here we're looking at a stereo image of some tubing that has an orbital weld, and on the edge of that weld you can see there's some excess material protruding from the surface. And in this case we might like to know how high that material is standing off the parent material. So we've applied a depth measurement where 3 cursors are placed on the parent material. I'm sorry, I'm not sharing my screen. Let me try that again. So stereo image, tubing with an orbital weld, excess material. We'd like to know how high that's protruding. So we've applied a depth measurement where 3 cursors are placed on the parent material and a 4th cursor is placed on the point of interest. The measured result, in this case 0.5 millimeters, is the perpendicular distance from that 4th cursor back to the reference plane established by those first 3 cursors. So if this were a traditional stereo measurement image, all you'd have to look at to assess the accuracy of this measurement would be this 2D image. And it's very difficult to identify any potential sources of error when all you have is a 2D image to work from. So fortunately, this is a 3D stereo image, and we have those other real 3D pieces that we can apply. So let's go into the measurement screen. And the first thing you'll probably notice is some colored banding here on the surface. So the green masked areas are showing points on the surface that are lying very close to the reference plane that was established by these first 3 cursors. The areas in blue are points on the surface that are very close to this 0.5 millimeters above that reference plane. So when we're doing this measurement, what we would expect to see would be a solid green band running along the top of the tubing, and then just a little puddle of blue on top of the excess material. So using this 3D surface mask, we can tell immediately that there's a problem with the way this measurement's been set up. So now I'm going to switch to the point cloud view. And in this view, if I activate a cursor, we can still see that 3D surface masking. And we also have this blue rectangle, which is showing us where in 3D space that reference plane has been established. So if we rotate the view to the side, you can see that that reference plane is set up at an angle relative to the top of the tubing. Ideally, that plane would be set up right up here along the parent material. So we can clearly see we've got a problem with the reference plane. And if we zoom in and look at the actual measured dimension, the 0.5 millimeters is this pinkish line going from that fourth cursor down to the reference plane. So you can see, instead of stopping at the parent material surface, it's going well down under the surface, and that's going to give us quite a bit of error in our measured result. So using these 3D technologies of the 3D surface mask and the point cloud view, we can tell immediately that we've got problems with this measurement. So now I'm going to go back and switch to an image where those cursors have been repositioned. And now when we look at the 3D surface mask, we can see that solid green band along the surface, which is what we would expect when properly placed cursors are here. And then the fourth cursor just has a small pool of this light blue around it. Also what we expected. And if I go back to the point cloud view, something else you'll notice is that we don't have a lot of noise or bumpiness on the surface, which can be a result of capturing the image from too far away or some of those other 3D data quality issues I mentioned. And we also can clearly see this excess material standing off the parent surface. So the system has been able to resolve that feature, which gives us a lot more confidence that the measured result, in this case 0.24 millimeters now, is going to be accurate. So using these tools, we can have a lot higher confidence in the accuracy of our measurement. So the final aspect of Real 3D was this dynamic advisory system. And this system looks at the type of measurement we performed, in this case the depth measurement, along with the measured result, 0.24 millimeters, and this max target distance, or MTD value. And that's telling us how far from the tip the furthest cursor in our measurement is. And so the system takes a look at these three aspects of our measurement and assesses whether the system is likely capable of making an accurate measurement at that distance and of that size. So if I move this fourth cursor, which I can do right here in the point cloud view, you'll see as my result gets a bit smaller that I get a message suggesting that I move closer for better results. So that is the dynamic advisory system, and it also gives us this orange outline around the MTD and result to indicate, hey, you know, you're pushing the capability of the system here. It might be better if you moved a little bit closer and took another image. So that is the overview of Real 3D. And at this point, I'm going to turn it back over to Mr. Danvers, who will walk you through the measurement examples.
Thank you, Clark. Hello, everybody. Thank you for joining in on this webinar. Yes, I'll be taking you through a number of, should we say, interesting examples or applications associated with a variety of measurements. I'll be really focusing on 3D phase measurement, not traditional or 3D stereo that you've heard Clark sort of provide an overview of. So yeah, I'll be spending the next sort of 20 to 30 minutes talking about these points here, weld inspections, pipe tube inspections, measuring missing sort of areas of material, for instance, going through that from a gas turbine inspection application, blade tip clearance, a relatively new measurement that is now available in 3D phase measurement. And yeah, just touching also before wrapping up an overview of something new that's coming in from a boroblending perspective and might also have applications elsewhere in terms of applying a circle gauge to determine the radius of an object in view. So that's a new measurement that's coming in later, this, as Clark was saying. And then a few minutes talking about 3D stitching. So yeah, I'll just share my boroscope screen. Bear with me, just clicking a few buttons. Very good. So starting off with a weld application. Here we have a previously saved image, 3D phase measurement image showing the inner tube, inner bore of an orbital weld within a tube. And the challenge here is to determine the maximum distance or maximum height of the weld bead. There's two options available on the boroscope, depth profile and area depth profile. Now I've just selected depth profile, and I'm just adjusting the point cloud on the boroscope so I can get that all in view. So I'm in the once having selected depth profile as the measurement type required, the user is invited to basically place 2 points on the curve, either on the image, either side of the weld. Now, the requirement here is really for the user, the operator, you, the inspector, to determine where on the image to place those cursors in order to determine what is the maximum profile. I'm just going to press and hold the text box just to flick back into metric from Imperial. And basically, you're then invited to kind of really adjust the positions in order to determine what you think is the maximum height along this profile. So there's really a need to sort of adjust the cursor points, wait fractionally to determine the actual measurement, to determine whether that's really where you want to take your measurement from. So that's depth profile, very quick and easy way to determine the height, whether it's above or below the plane of two cursors applied to the 3D phase measurement either side of the weld bead. By pressing onto the views, you have the option of having the profile view or a split point cloud view, whilst having the 2D on the left-hand side. So I'm really just comparing now depth profile against the other measurement type, area depth profile. So let's just do the same again, same image. In this case, selecting ADP, area depth profile. Let's just adjust that view again. So we were getting a value of approximately 1.9 millimeters. What I'm really wanting to demonstrate here by just taking you through ADP is by selecting the reference plane. In this case, you'll appreciate is curved because it's the inner surface of a tube, and then pressing the third point on the other side of the weld bead. The instrument is measuring the profiles automatically in the background of all of those profiles that exist within that area that's been selected by me. And it's automatically picking out the point here that, as you can see, of much greater than 2 millimeters, 2.4 millimeters almost, of the profile. Really a good way of really performing many measurements. And you'll hear another similar example later on in this session associated with blade tip clearance, where the instrument is performing many different measurements and showing you the position in this case where the maximum depth exists. As per depth profile, you also have the option to select the different views, split between point cloud and profile, for instance. Now, I'll quickly show you what, with this being area depth profile selected, you can select the measurement. And perform what I was just going to show you this demonstration. So here with the profile view selected, you can run the demo, as we say, and it's showing you, illustrating you all of the measurements that exist within that area that's been selected. So just to remind you, I went to page 2 on the soft keys, pressed options, and then selected run demo, and it's automatically running through those profiles. This is something that you can record on the device and play it back, for instance, frame by frame, if you so wanted to sort of determine the topography or the profile of those those welds within the area that's been selected. And since this is a profile that's proud of the surface, it's above the plane. If this was a depression, you can select below the plane, and then it'll determine exactly the same sort of calculation in terms of all of those measurements, and it'll give you the minimum, the position upon which the minimum point below the plane exists. In this case, you can appreciate it's moved to this position here. So here we have a good way of really giving you lots of information by virtue of the point cloud, in this case 3D phase measurement. Moving on to the next image that I have here, showing you a use case associated with determining the width and the height of this weld bead. So what you're looking at here, if I switch to my point cloud view, are two plates that are bonded together with the weld bead. This is a 90-degree sort of T-joint between two plates. And the challenge here is basically determine the width and the height of this weld bead. How can we do that on the boroscope today? So here's a case where by using the depth function, it's kind of I'd like to sort of describe depth in this capacity as being sort of a point to surface measurement type, not necessarily just depth. So what some of you might appreciate when selecting a depth measurement type, what you must do is determine the reference plane. So that's by selecting 3 points. And as Clark was saying earlier, sort of make good use of the 3D surface mask. Make sure you've got a good agreement between all of the points that you've got selected in your reference plane by determining sort of a good amount of a green surface that exists in there. And the fourth point, really from a depth point of view, is then projecting a distance, a length in this case, that projects above the point cloud. So if we go back to the full image. So here we're basically determining the height of the weld. And you might see on your screen the blue 3D surface mask that corresponds to all of the surfaces or the points on this image that correspond to this same distance, 3.94 millimeters. So here's a good example where you can sort of adjust the position of that cursor so that you're including all of the irregularities of this weld bead. So I'm just sort of fine-tuning the position. You can see as I move, it's making good use of that sort of projection of the blue surface. So what would this being a depth measurement, or it's very useful to basically do the same thing again, but in kind of reverse. Now add another measurement, pressing depth and determining your reference plane on the other surface. Let me just make an adjustment. So there's my reference plane. And now place the fourth point here. Again, let's just, I like to adjust that cursor just to include all of the weld bead. So what I've done is basically done the same again, 2 depth measurements now on this image. I flip back to the 2-dimensional screen or the full image. You'll see both presented in one shot. I know it perhaps is a messier screen with 8 cursors now positioned on the screen, but you see both reference planes and both measurements, in this case projecting 3.5 millimeters and almost 4.5 millimeters as associated with the width and the height. Go back to my point cloud. So here we go. You see it on the point cloud. You can switch to next measurement, and then you can see the other measurement there. So yeah, I wanted to bring this to your attention really because although it says depth on the boroscope, you can use depth in this case to measure a series of lengths. You know, in this case, widths and heights of a weld bead. Sticking to the same theme with inspections of plates and welds, my next use case here is inside the tube. Now, tube inspections, weld inspections. Sometimes it's necessary to determine what is the diameter of the tube. So you'll appreciate perhaps that there is no button here that says diameter. But again, we have here is depth, and bringing your attention to using depth, in this case, to determine the diameter of a cylindrical surface. So as I was describing to you earlier, depth can be projected as or considered as a point to surface measurement. So if I, in this case, project a very narrow reference plane, let's just straighten that up. So I've intentionally sort of made my reference plane very narrow in order to get a good projection from a narrow position that represents the edge of the tubing here. And the instrument projects 90 degrees perpendicular to that reference plane in order to detect or calculate the inner diameter of this tube. As you were shown earlier, it's easy to select multiple measurements, additional measurements, shall I say, on the screen. So let's do that. Another reference plane and another diameter calculated. Pressing and holding the text box takes me back to Imperial. And yeah, 0.614 millimeters for one measurement, inches, 0.6 inches for the next. So this is kind of almost 0.625, which it took me a while to realize, because I tend to work in metric, but that's almost 5/8 of an inch. And yeah, just as a reminder, flicking back to the point cloud, you can see both measurements. Let me just drag those boxes down so you can see them. Both measurements here projecting 90 degrees from a very narrow sort of reference plane from using the depth function to infer diameters on a tubing. Right, moving now on to gas turbine application. Here we have an image of a compressor blade with a sharp missing, the corner of the material missing. In this case, you'll see it as my mouse is moving across the screen. So this is usually something that cannot be done associated with applying cursors to a surface. If I do it in the traditional sense, if I press area, you'll appreciate perhaps when you assign your cursors around this surface, it's actually placing the cursors onto the abradable liner itself. And that's clearly not going to calculate an area of the missing material. So let's delete that. Now, we have this ability to, using 3D phase measurement, to assign a measurement plane. This allows us to place a plane and project it across the surface, across, in this case, the edge of the aerofoil, and allow us to place cursors on that measurement plane. So having assigned a measurement plane, it's now possible to select area and move your cursors now onto what is now going to be this measurement plane. So I'm going to make use of the magnifying glass that you see on the top right hand side of the screen. Just sort of micro position. Ooh, I didn't mean to do that. Let's move that cursor down. Let's try that again. And it's quite easy just to sort of select the points, press done, and with it being an area, it wraps that final cursor point to the original cursor point. I'm going to flip back to metric. So what we're getting here is a value associated with an area and the two sides, the sort of the adjacent and the opposite side of this right angle triangle almost. Now, if I flick to full image, there's my measurement image, there's my full image, here we go. So you'll see here, I can fine tune the position of the cursors on this screen here, and you might see on these blue, just adjusting the cursor so you can see the projection of these blue 3D surface masks here. So this allows us to make sure that we've got the right angle, the point. Obviously, that's missing material here. So where do we place that cursor? So make a good use of the 3D surface masks so that we've got good agreement between this surface and this angle of this missing material with the intact material on the edge of the aerofoil, and same along here along the tip of the aerofoil. So we've got good agreement of the 3D surface mass projecting along the plane. And yeah, so we're getting a good agreement. I've done this obviously a couple of times in rehearsal, so we're getting good agreement of 1.5 square millimeters. And just if I flip back to the 2D screen, you'll see the key associated with line 1 and line 2 and the corresponding lengths of those two lines. So that's the assignment of an area in this case by use of the measurement plane. Measurement plane can be obviously used for other measurement types. Again, something just to be aware of, that when you're assigning points on a cursor on the measurement plane, you've got to be very careful on where you place your cursors. It's because it's now inferring an area or the measurement associated with that measurement plane. So it's very important to make sure that your measurement plane is correctly assigned. I flick back to the measurement plane and onto the next image. So making sure those cursors in this case are very closely sort of positioned to where you're then wanting to perform the area measurement in this case. So sticking with the gas turbine application, my next example here is a similar blade, again within gas turbine, looking at a compressor blade. Here we want to just take you through blade tip clearance. I'll just run a short video, just show you in action as if it were live on the screen. This is obviously a pre-recorded video clip. Once you've got your probe set up in a nice static position, looking at your target, there are instances where it is necessary to carry out a blade tip clearance check on either some blades or all of the blades within a given stage. What you saw me doing was pressing the auto repeat button, toggling that from off to on, and then pressing the blade tip clearance button. And immediately you saw that point cloud being presented. So it happens very quickly. Within sort of 10, 15 seconds, you're then able to sort of save that image, flick back to the live state. And because auto repeat was assigned, once you press 3D measurement, 3D PM capture again, it'll automatically select blade tip clearance. And what you see here, it happens immediately. You don't have to press any additional buttons. You just press the 3D PM capture soft key, and there you have a series of projected lines that aren't shown, and it's basically presenting you the average, minimum, and maximum lengths between the tip of the blade and the corresponding shroud liner or abraidable liner. Rotate again. So within sort of 30 seconds, you're able to carry out very powerful measurements associated with this given surface. It's worth pointing out what I'm using here in this case is the green long-range 3D phase measurement tip. It has a much greater range to capture good quality point cloud information in comparison to some of the other tips that we have within our range. It's good to capture up to 150 millimeters or thereabouts, which is a good 6 inches from your target. So it's a really good example where using the long-range 3D phase measurement tip really captures a lot of good quality scene so that you can interrogate, in this case, almost the entire chord of this given blade set. Just come away. I'll show you the image that was saved from one of those sequences. I perform the measurement again, press measurement, and then blade tip clearance. So here we have one of those measurements from one of those blades that you saw captured within that video sequence. You can move the reference plane should you choose to want to, but you cannot adjust these 2 points here. So these correspond to the minimum and maximum points in terms of the greatest and the shortest lengths from the blade tip clearance. These additional points here and here on the trailing edge are the extremities, so the range upon which the measurements are taken. So as you move these cursors, the point upon which the minimum is calculated adjusts in this case. So as you extend it, you can see essentially the minimum is towards the back and the maximum is towards the front of the compressor blade. So as I change the span of those measurements, you can see the text box in the top left-hand side, the maximum is changing as I move that point there. So blade tip clearance, a very powerful measurement technique that saves an awful lot of time doing those measurements manually. If you are doing it all by eye, it's likely that you'll get different values associated with the minimum, max, and average that you get here. These correspond to many images, many measurements captured in this scene using the green long-range 3D phase measurement tip. So something that's coming later on this year, boroblending. In terms of, this is a technique that's widely adopted within the gas turbine industry in order to enable the continued operation of engines in service, whether it's aviation or land-based or marine-based, for instance. Boroblending is a process upon which the removal of defective material is possible in situ without disassembly of the engine. So a number of hours were taken, probably 4 or 5 hours taken to remove this material here and remove the site of high stress concentration associated with either a crack, a tear, or a nick. In this case, that was close to the tip of this aerofoil. There are emerging requirements associated with the shape of such blends. So what we have here is obviously a previously saved image of a boroblend. The length already determined by this point-to-line measurement that you see on the screen. So the length here, if you can see my mouse moving across here, is 3.594 millimeters, so almost 4 millimeters. So what I'm going to just show you in the next few seconds is this new feature where we're able to, oops, I didn't say, I meant add measurement, not next measurement. So this new tile that will be appearing on the boroscope screens for analyzed handsets is radius gauge. So this enables us to apply basically a circle of a given radius, or indeed a diameter, should the user want to assign a value associated with the diameter of the circle. So here I'm going to be placing a radius that is going to be twice the depth of the blend and infer whether or not the shape of this part, the lead out of the blend, corresponds to the acceptance criteria for this process. So I'm going to type in 3.94, and because I want the radius to be double the depth of the blend, so I'll multiply it by 2. You can see at the top of this keypad registering the answer 7.88 millimeters, and I want that to be a radius rather than a diameter, so I save it as a radius. And what you see on screen is a circle of that given diameter. This, you see on the top left-hand side, it says 7.88 millimeters. So now I'm being presented with a 3D point cloud view. I'm just adjusting the center of this circle such that the edge, so if I zoom in, the edge of my circle of that given diameter is placed on the lead out, as I would describe it, of this blend. And you can see here, although it's a nicely shaped blend lead out, it does not conform to this radius criteria. So this is a portion of material that would need to be addressed in order to blend out some more material that you can see between the actual blade surface and this magenta line associated with that radius of twice the blend depth. Flick to, you can see the corresponding image on the 2D view. What you see is good agreement of the measurement plane, and in order to highlight the appearance of this radius, some of that measurement, some of that 3D surface mass, sorry, the green shaded area is removed around here, as you can see. So you can move it around using the fine adjustment there. So that's radius gauge in terms of the application associated with boroblends on gas turbine applications. Take you back to the screen. So taking you through boroblending, blade tip clearance measurements, area measurements of missing material, depth profiles of weld inspections. Just a few more moments associated with now 3D stitching. This is a new feature that was incorporated in the software build that was released earlier this year in January. 3D stitching. This is a feature that's associated with 3D phase measurement enabled instruments. As the name would suggest, it enables you to perform captures, multiple captures to increase your area that you can view and measure. Once you've found a defect within an engine, for instance, it's necessary to then measure it. If the size of that defect exceeds one given field of view, traditionally multiple separate images would be captured and different images, measurements would be added together. Here's an example where now once we've got 3D stitching, you can perform that measurement in one captured composite image. There are also instances where it's necessary to determine the position of the defect, for instance, the distance from the blade root or blade tip, given a known point on that component, and that can also be a measurement or a distance that exceeds one field of view. So 3D stitching is a powerful feature that enables you to perform that task now on the instrument within one composite view. 3D stitching is not just available on the boroscope, it's now available within Inspection Manager 3.6 that was released. So that's now available from download from the Inspection Works store, or indeed it's included on the USB thumb drive for units that were purchased since March this year, and 3.6 was released. So yes, please make sure that you update your systems. It's available, included on the Analyze handsets, the MVIQ Flame Analyze models, and also available sort of as a la carte kind of pay-for feature for touch and inspect model. Just take you through a short demonstration on the boroscope for 3D stitching. So So what we have here is a number of 3 images, and quickly just showing you, these are separate images captured from a turbine blade. Here you can see, obviously in File Manager, they're saved images, but this could be done live on the boroscope, such that you acquire the image, move the probe, reacquire new images, and perform a stitched image, sorry. So here we have a stitched composite view of a turbine blade, and by flicking through to the second page of soft keys, you can toggle between your individual images, make sure you're happy with those acquired images, select stitched image, and you've got your composite image, in this case of a turbine blade. I'll just quickly show you, once you've pressed done, you now enter into the measurement state, and here's where it's very easy. Just perform a very simple sort of length measurement in this case. Just demonstrating you a measurement that would not be possible using some tips or some views of components, because it's not possible to capture the full scene. So there might not be room in the engine, or you might not have a tip that's a green long-range tip, or yeah, here we've got the stitched image performing a length measurement across all 3 images. So 3D stitching, very powerful tool. Come away from that. Very good. So, yeah, be aware of that. That's a great tool. Hopefully you can make use of in the future. Now, moving towards just the final quick poll question for you all. If you could just take a moment just to click on which you use most regularly in terms of the types of measurements that you use in your typical inspection workflow. Here you'll see all of the measurement types that are available for 3D phase measurement, which some of you have access to. I appreciate from the answers from your poll questions, some of you are using traditional stereo, for instance. So yeah, very much interested in the types of measurements that you perform in your task. Yeah, just click the appropriate button, give you a few more seconds. Okay, thank you. So a good range, so you're pretty much using all different types. So yeah, very much interested in what you make of radius gauge. That's a new one that is obviously entering into the family of different measurement types that's now available on the boroscope. So thank you very much. Pass you back to Tom Ward and invite you to ask your questions, and we'll spend the remaining time going through those. Thank you.
Yeah, thank you, Tom. Thank you, Clark. Really appreciate the time you spent here. And for everybody that's on the webinar, thank you for staying with us. And I hope that you've learned something today. I want to spend the next several minutes answering any questions that you might have. Maybe the first one, just letting you know, everything you've seen today, all of the software that we develop, and we try to develop a software build or an upgrade, if you will, on the Mentor Visual IQ at least once a year. And then that's where we're adding new tools like this radius gauge that Tom mentioned that hopefully can help you, and we'll continue to do that. And we want you to be able to use those. So if you have a Mentor Visual IQ in the field already, you own it, you use it, when you upgrade to the new software build that includes radius gauge, to use that example, you'll have the ability to use that for 90 days, for 3 months to try it out. And then if it's something that works well for you, you can go ahead and contact your local sales support, and you can purchase that if you want to use it in the future. And that's true of all the software that we have. And even when you buy a new video borescope, depending on the trim package that you buy, our Analyze system comes with everything, and then our Touch and Inspect system come with a la carte options. You will get all new software that you haven't been used before on your system. So if you've never had it on your system, that will also be available for 90 days. So keep that in the back of your mind that that's available for you to try out real time. Please use that. And with that, I'd like to go to some questions today. Let's see what we have here. Okay. From Scott, techniques or tools for stable photos in 3D mode. So if either the image is too far for measurement or unstable for a photo, Clark or Tom, do you want to take that one, or we'll reach back out with an answer, a more fully realized answer if you don't have all that in your head right now? Please take a stab at that one while I look through some other questions.
Yeah, I can perhaps chip in perhaps before Clark does. Yes, you'll appreciate the probe does need to be stationary for a good sort of 2 to 3 seconds in order to capture a 3D phase measurement image. So use of guide tubes, rigidizing tubes, or even the probe holder, the red plastic conical rubber probe holder that gets included in your probe when you purchase your probe from Waygate Technologies. I've actually got my red probe holder stuck into the engine in order to keep that probe very stationary, so you can be hands-free, you can be comfortable, and you can interact with the touchscreen on the handset without having to hold the probe with your hand. And even though your hand might be stationary, there is some quiver and movement, and so the instrument will detect movement and it will automatically reacquire additional attempts to capture a successful 3D capture. But if it doesn't, then you'll appreciate, obviously, that's where you get errors coming up because movement was detected. So, yeah, rule number one in pretty much any gas turbine inspection, from my perspective, is getting comfortable. And part of getting comfortable is sort of positioning that probe into a nice, stable position. So use of guide tubes, rigidizers, or even the probe holder is a good way to make that happen.
Yeah, and
Thanks,
I would
Tom.
add that if you have a place where you can attach a magic arm to the engine, if you put a gripper into the magic arm, then you can position that gripper right below an inspection port or a borescope port and hold the probe stationary that way. That can also work pretty well.
Yeah, thanks, Clark and Tom. That's good. Another question we have is, what's the primary difference, like the advantage, I guess, of 3D phase measurement over more traditional stereo measurement? I think you guys talked a bit about it, but maybe just expand a bit there on the difference and why 3D might be more useful when doing measurements.
Yeah, so as I noted earlier, the 3D phase tips, they have a 105-degree field of view, so a nice wide field of view, and a large depth of field with high optical resolution. And so they give a really nice quality image for general inspection. So a lot of applications where you might require changing tips between non-measuring tips and, say, stereo tips for making measurements. 3D phase tips can often be used to do that entire inspection. So it can be a very nice efficiency saver or improver. And the image quality is just really good with some of these 3D phase tips. We also have those 2 extra tips. We've got the orange forward viewing tip, which is a very close focus, 3 millimeter near depth of field. So if you're trying to measure very small indications, that's a nice option where you can get up very close. And then, as Tom mentioned in a few of his demonstrations, the green long-range 3D phase tip can work over a much larger area than any of our other tips, 3D phase or stereo. So you can get much higher quality 3D data from a larger standoff distance, or if you're needing to make measurements over a larger area, that's a great option.
Thanks, Clark. And for everybody on the line, looks like we still have a big group on the line here. That's great. I appreciate you hanging with us. Please chat in any more questions that you have, and know that you can certainly email us with questions that may come to you either later or if you're playing with the software and so forth. I do have another one here live now. How do I remove, Clark or Tom, how do I remove red surface masked areas from the measurement area to ensure accuracy in measurement?
Yeah, so this must be referring to pixels that are masked in red when you're making measurements, which indicates that at those pixels, we were not able to compute the 3D coordinate. And so, you know, a couple of things that might be helpful in those cases, if you're getting red masked areas where you want to place your measurement cursors. First, you know, adjusting the angle of the view relative to the surface. Sometimes if it's a shiny surface, for example, the glare in the projected pattern images on 3D phase or in the normal image for stereo may result in areas where we aren't able to produce 3D data. So adjusting the viewing perspective can be very helpful there. You know, getting closer often can help. And if you're making length or area or multi-segment type measurements, you can also use the measurement plane. So you can put down a measurement plane in areas, if it's a flat surface you're measuring on, you can put down that measurement plane as Tom demonstrated on the edge of the blade. And then you can place cursors of, say, your length measurement or your point to line in areas that were previously red masked, and those will be projected onto that measurement plane, and you can still make the measurement in those areas. So a few options there.
Yeah, thanks, Clark. That was a good one. I know we're running a little short on time. I have another one here, though, I'd like to get to, team. This one's asking the question about how do I get a better image or video of a combustion chamber? So it's full of coking. And because of the coking, it's reducing the light from the probe. So less shiny surface, which is a good thing, but maybe not enough light to be able to see as well as they'd like to. Some comments there?
Yeah, shall I chip in on that one? That's a good one. Lots of carbon obviously sucks a lot of light out from the boroscope tip, so it'll obviously appear very dark on your screen. So rule number one is, can you use do you have access to a larger diameter probe, and are you using the appropriate optical tip adapter on the end of your probe for your inspection? The larger the diameter of the probe, the more light you're going to get projected into that large cavity of the combustion chamber in this instance. And so an 8.4 will provide a much brighter shot, an image, and throw much more illumination or lumens into that cavity than the 6 or a 4 mil probe can. If you don't have access to additional sort of diameter probes, for instance, so you're fixed with your 6.1 millimeter option, for instance, which I can understand, are you using the right tip? Have you got a near focus tip, for instance, fitted? Do you have access to the far focus tip, or even the orange and blue ultra bright tip, in order to transmit more light into that cavity? So choice of probe diameter and choice of tip are sort of rules, associate the hardware rules that you'll need to apply. And then really, from a software perspective, make full use of the tools that you have on the boroscope. Number one is the brightness setting appropriately configured. Obviously, putting it too bright might over-illuminate and overexpose some of those target surfaces that you're wanting to look at. So make use of some of the tools and tips that you heard in webinar number 1 that you perhaps might have attended last week that talked about probability of detection. So a key feature is in that suite of tools that that were taken through in a live sense is toggling with dark boost. So press the dark boost button. There's a slider that then appears on the screen. increase that value, and that will illuminate those darker, far view sort of images much more. And that's a very useful tool, especially in those large cavity applications such as combustion chamber inspections. So a range of things that you can do from a hardware and software perspective.
Thank you, Tom.
Yeah, I'd also mention long exposure can be another knob. So increasing the maximum exposure time, you do get some blurring potentially as you're moving the probe with long exposure engaged, but it can really brighten an area if you get to sort of a stable position and you want to see into a large cavity. That can be helpful. So, and then we also have the gray forward view tip along with the orange and blue that Tom mentioned. So the orange and blue is a 65-degree tip, field of view. The gray is a 120. So if you want a wider angle, really bright tip, large aperture, bright optics, the gray is a really nice option. Smaller field of view would be the blue and orange.
Yeah, thanks, Clark. Thanks, Tom. Appreciate the answer there. So that's all of the questions that I have here on the deck. So we've answered those, I think. Any other questions, like I said, please reach out to us. Appreciate your time today. Please do us the favor of filling out the survey, letting us know that the content was what you wanted to see and that the format works, so we can adjust in the future if you need to see something different. And just lastly, once again, a big thank you. We appreciate you guys joining today. Goodbye for now.